What I'd like to talk about is a part of a larger study we're undertaking to understand some of the drivers of persistence in both low and high precipitation regimes. It's a collaborative effort with a number of colleagues from myself at the University of Colorado, as well as University of Southern California, University of California, Santa Cruz, and University of Hawaii. These universities broadly span the western part of the US, including Hawaii, which means the Pacific. One of the things we're interested in is to what degree the ocean perhaps controls some of the precipitation. I'll speak to that. One of the key problems I see is this disconnect between thinking about global warming and global temperatures versus what actually happens in perhaps a local farm where the idea of investment is very different from the idea of investment at the global scale. It's useful to know that as CO2 increases globally, the temperatures increase. But for a farmer, perhaps as a prototype local industry, how useful is that information? And I'm going to use that as sort of a basis for thinking about some of our work. I show here an example of one of the local industries. Here we have a vineyard, Oregon, Mount Hood there in the background. And of course, the industry here is the winemaking industry. And recently I was speaking to the owner of this property, and he pointed out their 2012 Pinot Noir is going to be really great. What's so good about the 2012? And of course, having mentioned this, I had to try out the 2011, the 2010, the 2009, just to make sure he was correct. And he is, he's right. It is very good, but the reason is tied to climatic anomalies. And in fact, 2012 turns out to have been a year where there were bumper crops, the conditions were just right, and the little Pinot Noir grapes grew particularly well. And in fact, the Pinot Noirs from across this district are going to be great for 2012. On the other hand, this year, again, in the same area of the Columbia, the cherry crops were horrible. And in fact, most of the cherry crops in this whole area had to be trashed. The cherries from this area, I was speaking to one of the packers who take the local cherries and ship them. It's amazing that within 24 hours of being picked from a tree here in Oregon, those cherries are put on a plane, taken to Asia, and you could have a cherry on top of ice cream in Tokyo that was picked in Oregon about 24 hours ahead of time. So it's an incredibly efficient transport market. However, that didn't happen this year for the most part because of climatic influences. And in particular, what happened with the cherries was there was a period of rather warm conditions, unseasonably warm conditions in April and May. Early May, there were a couple of rainstorms, and the cherries had come out. The cherries are on the trees, ripening, and the cherries have a little, I'm not sure how to describe, a little bowl shape in the top of them at the stem. Water trickles into there, and the water sits in the top of the cherry. What happened then was warm days followed, sunny days followed. The cherries don't behave well when this water sits on the top, and they split. Nearly the entire crops from this area split. As shown here, this is a pretty good example of some of the cherries being split, and these can't be shipped. This is not the kind of cherry you'd want on your ice cream in Tokyo. This cherry costs $0. In fact, they were ruined. So understanding how these sort of phenomena may occur have very significant local economic impacts, although they are in some ways ultimately tied to global scale drivers. I'd like to give another example here. We're looking at a map of the United States broken down by district, precipitation districts, showing the amount of precipitation above normal for this period, March to May 2011, as it turns out. There's a number of things one can draw from this, and actually initially I got interested in this map for the case of Texas, where it was really a very unusual drought. It was incredibly dry, and if you remember back to 2011 through New Mexico, northern New Mexico, there were huge big fires, and really we got interested in this precipitation anomaly where the precipitation is less than normal for the reason of the fires. But the thing that jumps out of this quite remarkably is if we look at some other places across North America at the same time, this place in particular in the northwest, we see that it was unseasonably wet. In fact, it was very unusually wet, and there were indeed floods through particularly eastern Washington through Idaho as well. Very unusual wet conditions, very heavy precipitation. The thing that's remarkable about this is that there's some degree of organisation here, that there's wetness in the northwest, wetness in the northeast, and dryness broadly in the southern parts of the US. There's some degree of organisation. So this is tied in some ways to large-scale atmospheric climate weather patterns. This is the sort of scale at which climate models operate, and operate quite well. This is the type of information one could get from a climate model on this scale. Climate models do not do as well at the scale of a cherry. They do quite well at the scale of continents. If we do look at some climate model projections, here's one here, we can also look at how we might expect precipitation patterns to change into the future. This particular figure comes from the 2007 IPCC report, and of course we're anxiously anticipating the next report, which will be released soon this year. What we're looking at is the number of dry days per year and how that number of dry days will change into the future. And by and large, the figure is red for the most part, or orange, which is saying there's an increase in the number of dry days. And in particular, if we look at the Pacific Northwest, it jumps out quite distinctively as the number of dry days increasing. This may be the kind of things result that cherry trees do not like. If there's one rainstorm amongst these dry days and there's an increase in the frequency of that, there's going to be more vulnerability to catastrophic failure of the crops. So this kind of information is actually valuable to the farmer on the ground. Now, one of the critical questions we should ask, however, of climate models is to what degree should we place confidence in these sorts of projections? And one of the ways we can get access to evaluating these models is to use the relevant sort of data to validate them. One of the things we've been looking at is using tree ring records, and in particular the chemistry of trees, to find out if the precipitation projections that climate models make for the next 100 years are robust. And if so, we can trust them more, and we can perhaps give information to farmers saying, let's worry about our crops. So it's good to take stock for a moment and ask, where are our robust facts? What do we know well, and what can we rely on in making our projections? Well, in terms of the sort of the economic endpoint, we know that both the amount and frequency of rain is critically important. We take this as a premise, and the question then becomes, why? Are there changes in the amount and frequency? And if so, what are the changes in the future? Well, we know quite obviously when it rains it's because weather systems are coming through. So changes in atmospheric patterns, wind patterns, particularly the jet stream, the large-scale wind patterns in the atmosphere, the weather systems will change, and these change with climate change. So by this reasoning, we already have the connection from our global scale climate models to something we know locally is critically important. We can use the climate models to evaluate these large-scale changes in weather systems, and we can relate that back to the frequency and intensity of the precipitation. We can obtain from both weather measurements, but also tree ring records and other sorts of past climate records, that these types of changes we're imagining here with weather systems are indeed occurring. And ultimately, what we might be asking is there evidence for these types of changes in weather systems in the past that give us an idea of the vulnerability to perhaps these catastrophic crop failures, as my case is giving us? So here's a record, or a number of records that we've recovered of the chemistry of trees. The tree rings themselves, the widths of the tree rings. Here's a picture of a tree with some rings. The width of the rings give us an idea how much the tree grew during a particular year. So it's a good measure of health of the tree. The tree's going well, it's growing, it's making a nice big tree ring, that's fantastic. What we're doing in addition is we can chop up the tree ring and we can analyze the chemistry of the tree ring to learn something else. Not just how much precipitation there was, but we can learn something about how the hydrology and how the precipitation has changed. Understanding the mechanisms by which the hydrology is changing, gaining that information and using that information allows us to state with more confidence how things may change in the future. If we understand the processes, we can be more confident in making predictions based on them. So for those who are curious, what we actually look at when I say the chemistry is we look at the abundance of oxygen isotope ratios in the tree rings, and we have a series of 4 trees here, and these are actually both from Northern California and Southern Oregon. And what we're looking at is a time series from about 1965 up to about 2005. We see that the tree records broadly agree. They kind of go up and down similarly. Would anyone like to guess why I put arrows on there? They're all El Nino years. They're all El Nino years. So we know that El Nino occurs about every 5, 6, 7, 8 years. And when El Nino arrives, there's very distinct atmospheric circulation patterns. The weather systems are different, and so too the precipitation patterns are quite different. Actually, the wind patterns are quite different too, and those two are related. So what we see here, over this 50 or so years, 40 years, there are distinct changes in the trees, and we know they're related to very large-scale changes in atmospheric circulation, and El Nino, of course, is an oceanic phenomenon. So it's really telling us something about the large global scale climate, and we're seeing that with individual trees. The trees are there, and they notice these changes in the precipitation. If we think for a moment about why these records may change, one of the things that we work hard on is trying to figure out exactly how this works. What are these mechanisms? How do we know that these trees are giving us a good indication of precipitation? Importantly, what we're interested in is knowing how the weather systems have changed. If we understand how the weather systems have changed, it gives us an idea about the vulnerability of weather system changes in the future. So if we can indulge ourselves for a moment about understanding why El Nino jumps out distinctively, it's really 2 things that jump out for us. The upper panel here on the left is showing a cartoon of what the jet stream, for the most part, is like during an El Nino condition. And the lower one here is showing us the antiphase. When we don't have El Nino, the other extreme is La Nina, where the circulation patterns are somewhat the opposite. So what we're seeing in the tree ring records is really an imprint of these 2 differences. I actually want to point out 2 features on these. During La Nina, which is perhaps one extreme, there's a greater frequency for storms to move from the central Pacific and hit the coast. You'll recognize these from the TV weatherman, that when there's very heavy precipitation events and there's these deluges and often local flash flooding on coastal mountains, these are often called atmospheric rivers. Another word or another phrase for these, if they happen to come across Hawaii, they're often called the Pineapple Express. I teach classes in climate in Colorado, so I often make a point to make jokes about how the weather in Portland and Seattle is quite bad because you get hit by these pineapple expresses on the coast. Of course, we don't get them in central Colorado. So this is something that's quite distinct about La Nina, and actually it turns out there's very low, very dense cloud. This is very, very high precipitation totals. On the other side, we have El Nino, where I've made up this new term, the maple syrup express, perhaps, comes from Canada. The moisture arrives from the north. The clouds tend to be quite high. The precipitation is more intermittent, and it tends to be lighter. So both of these types of changes occur during El Nino, La Nina. This is what we're seeing in the tree ring record. But importantly, the changes we see with global warming are not unlike the difference between these 2. There's a tendency for the climate to look a little bit more like El Nino as time goes on. So the trees may tend to look more like one of these records. Now, we know also that these are telling us about differences in weather systems, the differences in weather systems giving rise to changes in the amount and frequency of precipitation, and that is what the cherries and trees care about. So perhaps one of the questions one might ask of our tree ring records is sort of how sweet is the pina colada if you put a whole bunch of maple syrup in your pineapple juice? That's what the tree's looking at, perhaps. I don't know. So here's another record, and I like this record in particular. This is a relatively fresh record off our machines analysing the tree cores. It's a record that goes a little bit further back. Here's year 2000, back in time to about 1887, I think is the first one. And again, we're looking at the chemistry, the same isotope ratio of the tree cellulose itself. And we see that there's a great deal of variability with some degree of trend here over the last 100 years. I would point out that this is a single tree. It's not necessarily representative of all trees, but it illustrates a number of things. This tree had a very different experience about 100 years ago from the experience it had since. There's perhaps some trend here, but we're really seeing some kind of dramatic shift. And why this is a great example is something very distinctively different has been happening to this tree in the last decade or so. So exactly what this is a very interesting question. If we think about our cherry trees, however, we see sort of the directions here based on these changes in the weather patterns. A downward trend is more towards an El Nino type pattern where it's the conditions with the maple syrup moisture that's coming in and more intermittent precipitation, the kind of things that lead to cherry splitting and failure of those crops. So from this record alone, we could imagine back 100 years ago, well, the cherries were great. There was probably better conditions. I'm paraphrasing a little bit, perhaps, but there is some quite distinct changes in the climate that lead to different outcomes for agricultural practices. So a question of adaptation is one of thinking about crops that could perhaps lead to more resilience of those agricultural economies. I have a little note down here, somewhat to remind myself as well, that about 100 years ago was a period where a lot of the sort of water-driven economy of the Pacific Northwest was established, including the dam systems and transportation, as well as vegetable growing. So if we come back to our map, we see this idea of organisation, which is largely tied to large-scale phenomenon in the atmosphere and the climate system. Some of this can be robustly projected, yet the smaller scale details are things that need to be interpreted, and perhaps we need to seek evidence for these in records like the tree cores, which I think we have. Just to wrap up, here's some delicious looking cherries. These are the kind you'd find on the top of the ice cream in Tokyo. If we think about this idea of resilience, we also need to understand the vulnerability and risk. Some of that we can obtain from these past records, but also need to be combined with our state-of-the-art tools to understand perhaps the changes in the climate system that go alongside our records. Thank you.